Hello and welcome. My name is Mahmoud Nazal, and my presentation is titled Multi-Instance Adversarial Attack on GNN-Based Malicious Domain Detection. This work is jointly conducted by New Jersey Institute of Technology and the QCRI at Hamad bin Khalifa University in Doha, Qatar. Let us begin with a flashback on graph neural networks or GNNs. Those are machine learning models that extend deep learning to handle graph structured data. By doing so, they combine knowledge from both local entity information as well as relational information across multiple entities. And by doing this, GNNs have been shown to achieve the state-of-the-art performances in a wide array of applications, ranging from traffic analytics to drug discovery. However, this is not, in fact, the case yet with security critical applications due to the fact that GNNs, just like many other DL and ML models, are inherently vulnerable to adversarial attacks of different types, whether it be at the node level, the graph level, the edge level, or at the multi-instance or multi-node level, uh, as done in this work. This work considers the adversarial robustness of GNNs in a particular application, which is malicious domain detection or MDD, which is indeed the process of inferring the maliciousness of a given internet domain, that is to say, whether it is associated with cyber attacks or a benign one. This process has been technically conducted utilizing public data and mainly DNS logs and, if available, enterprise level data. And at its core, MDD is in fact a guilt by association process. And this is done by mainly constructing a so-called domain maliciousness graph where different internet domains and IP addresses and entities of other types and relations are used to constitute the so-called DMG. And at the end of the day, some mechanism is utilized to infer the maliciousness of unknown internet domains from that of known ones. And GNNs have been recently shown very promising and highly performing as a framework for conducting this MDD business. And the process, as seen pictorially here, starts with DNS logs. Then after that is the DMG construction, and we can consider, for example, the following graph schema, combining domain, IP, and the client nodes with different edge types. And afterwards, a GNN model is trained to classify malicious from benign internet domains. And then it is in the inference time, it is utilized, such a model is utilized to decide upon the maliciousness of a given internet domain with or subject to providing a computational graph that surrounds that particular node, and at the end of the day, it will decide whether it is benign or malicious. As for the contributions in this work, we present the following ones. Indeed. Number one is a new multi-shot or multi-instance adversarial attack, which is conducted at the subgraph level. And it has the following features of being stealthy and practical in the sense that it is a black box attack and does not assume prior knowledge neither about the graph nor about the target model to be attacked. We also provide theoretical and empirical establishments of the insufficiency of the existing adversarial attacks to be conducted or to be forged in the context of GNN-based MDD. And we also provide experiments with real-world data. We characterize the threat model of the attack by the adversary's goals, knowledge, and capabilities. So as for the goals, the adversary aims at protecting or evading the detection of multiple nodes that it has, while having a minimal effect on the non-adversary nodes as pictorially represented in this graph. So this is the ultimate goal, which is to stealthily evade the detection of all adversaries' nodes. As for the knowledge, the adversary is assumed to know only the nodes in its own subgraph, and to assume certain commonly used edge types or link types across them. However, it is not assumed to know the remaining subgraphs in the DMG, neither the target model architecture or parameters as well. So this is in fact a black box attack. And as for the capabilities, the adversary is assumed to manipulate some certain features of the domains in its subgraph and some uh, some edge types in that subgraph. Here we review the main motivation for this work, which is characterized by the insufficiency of existing adversarial attacks on GNNs for the purpose of attacking GNN-based MDD. So here we characterize the insufficiency in terms of being of low evasiveness as well as of low effectiveness. So this is the case where we represent existing approaches for adversarial attack by repeatedly applying them on each and every one of the adversarial nodes. However, as seen here in terms of the attack effectiveness, the attack is shown to have or to exhibit a diminishing nature as the number of attacking domains is increased. This leads us to the following formulation of the problem of adversarial attack in the context of GNN-based MDD, where we cast it as a two-objective optimization problem. The first objective of this optimization problem is that for every adversary's domain node, the attack or the perturbations gained by the attack should help bypass that particular node. Secondly, the impact or the effect of those perturbations on the neighboring adversary nodes should also be positive and contribute actually to their evasion of the model. And accordingly, we formulate and then derive a closed form solution for the optimized perturbation at those nodes. And that solution happens to be a weighted sum of two components, and each one of them corresponds to one of the aforementioned two objectives. So overall, the fundamental objective is to saliently and collectively bypass the detection for all the adversary nodes. Here we expose the solution that we obtain at the end of the day, which has the aforementioned two components, where each one of them corresponds to one of the aforementioned attack objectives. Now let us present the proposed multi-instance adversarial attack algorithm dubbed Minta and how it is used to craft practical adversarial attacks on GNN-based MDD. Well, the process first off requires the availability of a surrogate model, and it can be obtained as follows. So starting from a certain set of training data represented in the shape of a DMG, we query the target model in order to be able to label some of the nodes in that DMG, which is then used for the training of a surrogate model that is obtained at the end of this training process and used to craft the attack as follows. So the process begins with the adversary constructing an estimate of its own subgraph, and then it uses the already trained surrogate model as well as the Minta algorithm to optimize the perturbations at the adversary's nodes, as can be seen here. Then after that, such perturbations are going to be implemented practically so that they will eventually appear in the DNS server. And this characterizes the adversary's scope. So at the end of the day, the perturbations conducted and implemented by the adversary have already been injected in the DNS server, which is read simultaneously by the defense entity, and that such an entity constructs a DMG. And the interesting thing here is that without knowing the full DMG, the perturbations aimed at or intended by the adversary would eventually appear in the DMG, and they will be utilized to bypass the actual target model. And this characterizes the target MDD's entities scope. As we can see here, it is the availability of the DNS servers that enables this attack to happen in the first place. And speaking of the perturbations, those can be implemented practically, and they can appear, of course, as planned by the adversary in the DNS logs by conducting simple name edits and or IP resolution changes. And those are easily conducted by any domain owner, being the adversary in our case, as we can see in those numeric examples. So at the end of the day, by manipulating the domain name and the IP resolution, the adversary is able to manipulate both the edges across the entities, that is to say the domain nodes, and their own local features. Here we arrive at the experiments, and I would like to present the experimental setup, the target, including the target model, and highlight the main key findings in the experiment. So, as for the target model, it is an HGNN approach, which is one of the state-of-the-art GNN-based MDD approaches and utilizes both public and enterprise data and has a state-of-the-art performance and has been commercialized. As for the dataset, we have also uh, a real-world dataset with representative scale and statistics, as we can see here. And that dataset combines both publicly available DNS data and also enterprise data. And for the schema of the DMG, we adopt the schema proposed by the authors in the GNN paper. And for the baselines, we compare the proposed Minta algorithm with node feature focused attacks as well as edge feature focused attacks, representing the state of the art in adversarial attacks on GNN, generic GNN models. As for the metrics, we employ two main metrics. Number one is the attack success rate, characterizing the ability of the attack to bypass the detection, and the higher is the better. And secondly is the negative flip rate, or NFR, which characterizes the side effect of the attack, and the lower is the better. Here we observe the results of an experiment where feature perturbation alone is applied. As we can see here on the attack summary plot, Minta is able to result in evading the detection of the vast majority of the adversary's domains, while having a negligibly small negative impact on other adversary nodes. And this result is seen here at the instance where all adversary nodes are included in the attack. And generally speaking, as more and more adversaries nodes are included in the attack, it is becoming more and more successful, especially in terms of the ASR. Here we observe the performance of a combined attack where both local features as well as edges across adversary nodes are simultaneously manipulated by the proposed algorithm. And we can see that combining those attacks generally has a similar behavior to the aforementioned experiment where only features are considered. However, the attack is more successful in terms of both metrics, the ASR as well as the NFR. Here we can see a baseline comparison where we compare actually the proposed algorithm with feature-centered attack as well as edge-centered attack, and it can be observed that Minta is more superior to both attacks in terms of both metrics. In conclusion, we have proposed Minta, which is a new adversarial attack that reveals a new security threat to GNN-based malicious domain detection, and it is practical in real-world settings and easily applicable. And it can be also integrated to other GNN-based AI models in other applications, namely security critical ones. And it has been shown to outperform the existing attacks And in other experiments in the paper, we show also that this attack is highly scalable with reasonable cost. This concludes our presentation. And on behalf of the team, I would like to thank you very much for your time and consideration. And this is a link, a QR code link to the implementation and the artifacts as well as the data set and the contact information of myself. Thank you very much.